Hello everyone, I am Dr. Miracle Sreshth and you are watching Allied Chemistry, and today's topic is law of mass action. We will understand today what is law of mass action, and we will apply this law of mass action to the equilibrium condition. Equilibrium condition, we already learned this thing that when any reaction is going on and the speed of the reaction to make the product and the speed of the reaction to make the reactant back in the reversible reaction. तो अगर आपकी रिएक्शन में फॉरवर्ड रिएक्शन की रेट इक्वल हो जाती है टू द बैकवर्ड रिएक्शन की रेट, सो दैट इट अपियर्स कि आपका रिएक्शन चल ही नहीं रहा है. फॉर एन एग्जाम्पल, अगर मैं 2 स्टेप आगे बढ़ती हूँ लाइक दिस एंड देन आई कम बैक टू 2 स्टेप्स, इट मीन्स the number of steps I forwarded, I came back in the same number. That means I did not move. So what will be the ultimate result that you will observe? You will just observe that I have done nothing. I have not moved at all. Why? Because the number of steps I have taken ahead are the number of steps I have taken back. Same way, this is happening with the reaction at the equilibrium. What type of reactions? जो reactions रिवर्सिबल होते हैं वही पीछे आ सकती हैं. दैट मीन्स द रिएक्शंस विच आर रिवर्सिबल इन नेचर मूव दिस वे टू मेक द प्रोडक्ट, मूव दिस वे टू मेक द रिएक्टेंट बैक. एंड व्हेन द रेट of the formation of product become equal to the rate of the formation of reactant, that state we can assume, that state it appears that nothing is going on because product भी उतने ही बन रहे हैं और reactant भी उतने ही बन रहे हैं. उस स्टेट को हम बोलते हैं इक्विलिब्रियम स्टेट. तो व्हाट वी विल डू इज वी विल अंडरस्टैंड व्हाट इज लॉ ऑफ मास एक्शन, फिर हम उसे अप्लाई करेंगे टू द लॉ ऑफ टू दिस इक्विलिब्रियम स्टेट. शुरू करते हैं लॉ ऑफ मास एक्शन. जस्ट अज्यूम कि हमारी रिएक्शन है ए प्लस बी विच इज गिविंग यू प्रोडक्ट्स. ठीक है, सो दिस इज द रिएक्शन वेयर द A moles of A and B moles of B are reacting to form product. Now, what Goodberg and Weiss said, they have given this concept of law of mass action. So let us understand what he said and in what terms he said. So what he said is that rate of the reaction is directly proportional to the active masses of the reactant raised to power their stoichiometric coefficient. If there are two, so the product of the active masses of the reactant raised to power their stoichiometric coefficient. So according to Goodberg and Weiss, rate of the reaction is directly proportional to the product of active masses of the reactant raised to power their stoichiometric coefficient. यहाँ पर active mass जो term है ना, this active mass means कि the mass which is active means which is changing at all, that is called active mass. यहाँ पे most of the time what we do is we take the concentration in the moles per liter. तो most of the time हम लोग active mass की बजाय we take the concentration mass ना लेके moles लेते हैं. तो this is what the law of mass action. So let me repeat it. Law of mass action says that product of the rate of the reaction is directly proportional to the product of the active masses of the reactant raised to power their stoichiometric coefficient. I hope this is clear to you. If I remove this proportionality constant, so I can write it as rate is equal to this K I am using as a proportionality constant, and just because this is constant, it is a special constant which is not going to change for a particular reaction at a particular temperature. तो ये fix रहेगा. So this is what it turns into A raised to power A and B raised to power B. ठीक है. So this is what constant, and the name of this constant is special. This is velocity constant, or it is also named as rate constant. Okay, so just take care this thing that rate and rate constant, these two are different things. Rate depending on the concentration of the reactant or the active masses of the reactant, but this K is fixed for a particular reaction. ये कभी चेंज नहीं होता है. रिएक्शन के लिए अगर आपका कोई भी रिएक्शन है, उस पर्टिकुलर रिएक्शन का K at that particular temperature is always fixed. ठीक है. So this is called law of mass action. Okay. Now just let us apply this particular concept to the equilibrium state. And what we know about the equilibrium, one thing we are clear about the equilibrium, that is for the equilibrium, forward reaction rate is equal to the backward reaction rate. Let us apply this concept one by one. Suppose now I am taking a reaction in which A and B are reacting to form C moles of C and D moles of D. So these are the product this time and these are the reactant. वहाँ पे हमें ज़रूरत नहीं थी तो हमने नहीं लिखा था. This time I am clearly indicating you क्योंकि reaction हमारी U भी जाएगी. तो that means कि मुझे पता होना चाहिए. This sign is indicating what? Reversible reaction. This two-headed arrow. Okay. So this is product and these are reactant. Fine. Now let us apply this law of mass action to the equilibrium state. So let us understand what happens at the equilibrium state. If I apply this as a reactant in the forward reaction. So if I write down the rate of forward reaction. For the forward reaction, according to law of mass action, rate of forward reaction will depend on Kf. यहाँ पे I am indicating here Kf because it is the coefficient for the forward reaction. So this K is the coefficient, this K is the velocity constant for the forward reaction, and A raised to power A, product of A and B raised to power B for the forward reaction. If this reaction comes back, so definitely it will come back because it is a reversible reaction. So rate of backward reaction I can write it as backward. ठीक है, reaction. कैसे लिखें? Rate of backward reaction will be equal to velocity constant for the backward reaction and the concentration of the reactant. अब this time now just observe, just consider this reaction going to the backside. When it is going to the backside, these are the reactant and this becomes the product क्योंकि ये हैं और ये बन रहे हैं. So what we are going to write down? The concentration of the reactant for the backward reaction, C raised to power C and D raised to power D. ठीक है. Now what happens is at the equilibrium, only at the equilibrium, rate of the forward reaction will be equal to the rate of the backward reaction. तो मैं इन दोनों को equal रख देती हूँ. ठीक है. So can I write it as rate of forward reaction will be equal to rate of backward reaction. अब इनको बराबर रखिए. So what is happening? Kf A raised to power A, B raised to power B equals Kb C raised to power C and D raised to power D. Fine. Kf, I am just keeping this B, Kf upon Kb, and I am shifting this A and B product to the downside. So this is Kf upon Kb in the format of this. Kf upon Kb I am doing this. So this is C raised to power C, D raised to power D divided by A raised to power A and B raised to power B. ठीक है. Now this Kf and Kb, this is given a special name called Kc. Kc is called equilibrium constant. So what is this? Equilibrium constant. This is the ratio of the forward and backward reaction, velocity constant of the forward and backward reaction. I hope it is clear that when we have taken these two forward and backward reaction rate, we have made them equal to each other and then we convert it into Kf upon Kb form, and then this Kf upon Kb, this is replaced by a constant called Kc, and this is called equilibrium constant. Now rather than writing down this Kf upon Kb again and again, what we will do is we will write it as Kc equals C raised to power C, D raised to power D divided by A raised to power A and B raised to power B. And this expression, you know what? This expression which we have written here is called law of chemical equilibrium. Okay, so it is clear to you how we are going to express it. Now let us define this law of chemical equilibrium. So first thing is, this is all happening at the constant temperature. So we will define it at the constant temperature. तो ध्यान से सुनिए, at the constant temperature, ratio of the product of the equilibrium concentration of the reactant and the product raised to power their stoichiometric coefficient is a constant, and this constant is called equilibrium constant. This is law of chemical equilibrium. Clear to you? So how we are going to define it and how we are going to express it. Now just assume that our reaction is a gas phase reaction. थोड़ा सा एक variation है, that is we are taking this time that the reaction is gas phase reaction, means the reactant as well as the product are gaseous in state, and we know that when the reactant and product are in gaseous state, we don't take the concentration in the moles per liter, we take it in the pressure. We assume the pressure of the reactant, we consider the pressure of the reactant, and then we find out the amount of the gas present in that particular reaction. ठीक है, या कैसे प्रोसीडिंग हो रही है, द कंसंट्रेशन कैन बी इजीली कैलकुलेटेड यूजिंग द टर्म पार्शियल प्रेशर ऑफ दीज गैसेस. तो अगर ये रिएक्शन आपकी गैसियस स्टेट में है, देन व्हाट वी हैव टू डू, देन वी आर नॉट गोइंग टू यूज दिस टर्म Kc, क्योंकि Kc में दिस C मीन्स when the concentration is taken and then the equilibrium constant is calculated. But when we are taking the pressure of the gases, because we are considering the gaseous phase and we are calculating the pressure, and then how we can find out the equilibrium constant. So the equilibrium constant for the reaction which is in the gaseous phase can be written as pressure of the product Pc. C is the product and the pressure of the C will be Pc raised to power is stoichiometric coefficient and multiplied by pressure of the another product raised to power, its stoichiometric coefficient, divided by reactant, pressure of the partial pressure of the reactant raised to power their stoichiometric coefficient. So I am writing here Pa raised to power A and Pb raised to power B. So I hope it is clear to you that Pb is a term, Kb is the term given for the equilibrium constant at the for the gas phase reaction. So this Kp we are considering at the pressures, and for the Kc we are considering these molar concentration. Concentration are kept in the square bracket. Always remember, change in concentration square bracket में when we consider the concentration. So this is called Kc. C means here concentration. जबकि यहाँ पे pressure लिया है तो pressure को आप concentration वाला symbol में नहीं रखेंगे. So this is Pc यानी C का pressure raised to power its stoichiometric coefficient, isn't it? So this way we can consider Kp and Kc. These are the two terms we have to understand here. Is it okay? I hope now you are very clear what is Kp and what is Kc, and why we are doing this. We are applying the law of mass action so that we can consider when the equilibrium is reached, because the equilibrium, once equilibrium is reaching, you cannot proceed the reaction to the forward direction, क्योंकि reactant and product stop, like the amount will be constant that time. तो अगर अमाउंट कांस्टेंट हो जाएगा तो यू कैन नॉट प्रोसीड इट टू द राइट हैंड साइड यानी टू द फॉरवर्ड साइड, और आपको क्या चाहिए, आपको प्रोडक्ट चाहिए. तो यू हैव टू अंडरस्टैंड हाउ दिस Kp कैन बी चेंज्ड, या ऐसा क्या करें कि Kp थोड़ा सा चेंज हो जाए सो दैट आपके प्रोडक्ट्स ज़्यादा मिल जाए. बल्कि अल्टीमेटली इफ इफ योर Kc इज मोर मीन्स द प्रोडक्ट्स आर more. तो हम ये चाहेंगे for the commercial preparation we will require this thing that C and D should be higher. अब ये कैसे होगा, that will be understanding in this chapter, but I hope it is clear to you what is Kp and what is Kc. Next वाले वीडियो में I will let you know what is the relationship between the Kp and Kc. Very important क्योंकि एग्जाम्स में ये काफ़ी आता है. So if you like this video, please hit the like button, share it and subscribe my channel.